Far beyond the orbits of Neptune and Pluto, past the frozen architecture of the Kuiper Belt and the scattered disk that lies beyond it, something vast and almost impossible to fully picture drifts in near-perfect silence: the Oort Cloud. No instrument has ever photographed it directly. No probe has entered it. No human-made object has even come close to its edge. What we know of it comes from inference, drawn patiently from orbital mechanics, from the physics of gravitational scattering, from the slow evidence carried inward by comets that have traveled unimaginable distances to reach us. And yet, the Oort Cloud is real as any feature of the solar system we've ever mapped. Its scale is simply so extreme that grasping it means setting aside almost everything ordinary experience has taught you about distance. To feel where the Oort Cloud begins, it helps to start closer in. The inner solar system, rocky planets, asteroid belts, fits within roughly 5 astronomical units of the Sun. 1 astronomical unit being the average distance between Earth and the Sun, around 150 million kilometers. The gas giants reach out to about 30 AU. The Kuiper Belt, that wide ring of icy debris and dwarf planets beyond Neptune, stretches from roughly 30 to 55 AU. Beyond that lies the scattered disk, a diffuse region of bodies with highly eccentric orbits, nudged long ago by Neptune's gravitational pull. And past that, the solar system seems to simply fade. The density of objects drops away. The sun's light dims toward a brilliant but very distant point. The sun's light dims toward a brilliant but very distant point. Then, beginning somewhere between 2,000 and 5,000 AU from the sun, the Oort Cloud begins to emerge. Its inner region, sometimes called the Hills Cloud, after astronomer Jack Hills, who formalized its theoretical shape, isn't quite a sphere. It's more like a thick, flattened torus, still shaped by the gravitational plane of the solar system's disk. But further out, past perhaps 10,000 AU, the cloud opens into something vast and roughly spherical, extending outward to distances of 50,000 to 100,000 AU from the sun. Some estimates push that outer edge even further, to as much as 200,000 AU, which translates to more than 3 light years, nearly 3/4 of the way to the nearest star system. These numbers aren't just large. They represent a genuinely different order of physical reality. Voyager 1, the fastest object humanity has ever launched, is traveling at roughly 17 kilometers per second, fast enough to cover more than 1 million miles every single day. At that speed, it won't reach the inner edge of the Oort Cloud for another 300 years. To cross the full extent of the Oort Cloud, from its inner boundary to its outer edge, Voyager would need to maintain that velocity for approximately 30,000 years. The whole of recorded human civilization, from the earliest Sumerian cities to this present moment, would need to repeat itself more than 3 times over before that crossing was complete. The Oort Cloud doesn't simply surround the solar system. It buries the solar system
inside a structure of almost geological patience. The cloud's origins reach back to the very beginning, roughly 4.6 billion years ago, when the solar system was still forming and the inner regions were chaotic and violent. The gas giants were growing quickly, accumulating mass and gravitational influence. Icy bodies that had formed closer in were flung outward by these giants, by Jupiter especially, whose mass alone exceeds that of every other planet combined. Through countless near encounters, these icy planetesimals were sent out on trajectories of enormous eccentricity, shot toward the far reaches of the young solar system. Over millions of years, the slow differential pull of the Milky Way's disk, what astronomers call the galactic tide, and the subtle gravitational nudges of passing stars began to work on those elongated orbits. Gradually, the most distant bodies had their perihelion distances lifted, their stretched ellipses reshaped into something closer to a spherical distribution. The Oort Cloud was the result, a vast reservoir of perhaps billions of icy bodies, loosely held by the sun's gravity, arranged in a sphere so immense that the sun at its center would appear as nothing more than a slightly brighter star. That looseness matters. At the outer edges of the Oort Cloud, the sun's gravitational hold has weakened so profoundly that it becomes roughly comparable to the gravitational pull of the nearest neighboring stars. At those distances, objects exist at what astrophysicists sometimes describe as a gravitational watershed, a place where the competing influences of our Sun and the broader stellar neighborhood are nearly balanced. A star passing within a few light years is enough to disturb an Oort Cloud object's orbit, sending it spiraling slowly inward until, eventually, it becomes visible in the inner solar system as a long-period comet. Bodies like Hale-Bopp, which traced a journey of roughly 2,700 years in its last orbit, are its messengers, flung inward by stellar encounters or the slow cycling of the galactic tide. They carry something of the cloud's silence with them as they move. It's this fragile gravitational binding that makes the Oort Cloud a genuine threshold. Within its inner boundary, objects orbit the Sun in paths that, however eccentric and elongated, remain closed. They'll return, eventually, drawn back by the Sun's authority. Beyond the outer edge, that authority gives way to the interstellar environment. Objects that drift past this point aren't captured by passing stars so much as simply released, untethered from any particular sun, joining the slow and sparse population of free-floating bodies that wander between the stars across thousands of light years. The outer boundary of the Oort Cloud is, in the most literal sense, the last edge of the Sun's gravitational territory, the place where the solar system quietly ends. The cloud's origins reach back to the earliest moments of the solar system's formation, roughly 4.6 billion years ago. In those first chaotic ages, the inner solar system was a place of violent upheaval, the young gas giants welling with accumulated mass and drawing space around them into motion. Bodies of ice and rock that had formed in the warmer inner regions were caught in the gravitational pull of these giants. Jupiter, above all, whose mass outweighs every other planet in the solar system combined. Through countless near encounters, these icy wanderers were flung outward on vast, sweeping paths, sent tumbling into the farthest reaches of the proto-solar system. Over millions of years, the slow differential pull of the Milky Way's disk, what astronomers call the galactic tide, along with the subtle gravitational nudges of passing stars, began reshaping those elongated paths. Gradually, these forces lifted the closest approach distances of the outermost bodies, drawing those long ellipses towards something more like a sphere. And so the Oort Cloud formed, a vast reservoir of perhaps billions of icy bodies, held loosely by the sun's gravity, spread across a shell so enormous that the sun at its center would appear as nothing more than a slightly brighter point of light among the stars. That looseness matters. At the outer edges of the Oort Cloud, the sun's gravitational hold has grown so faint that it's nearly indistinguishable from the pull of the nearest neighboring stellar systems. At distances somewhere between 50,000 and 100,000 astronomical units, objects in the Oort Cloud exist at what some astrophysicists describe as a gravitational watershed, a region where the sun and the surrounding stars of the local galaxy pull in almost equal measure. A passing star at a distance of just a few light-years is enough to nudge one of these objects inward, sending it drifting on a long arc toward the inner solar system, where it eventually becomes visible as a long-period comet. The Oort Cloud is not a still and silent place. It's a living interface, constantly responding to the slow rhythms of the galaxy around it. The long-period comets that occasionally sweep through the inner solar system, bodies like Hale-Bopp, which traced a journey of roughly 2,700 years in its last orbit, are its wanderers, shaken loose by stellar encounters or the patient cycling of the galactic tide. It's this very fragility of gravitational binding that makes the Oort Cloud a genuine threshold. Inside its inner edge, objects orbit the sun on paths that, however elongated, remain closed. They'll return eventually, drawn back by the sun's authority. Beyond the Oort Cloud's outer edge, that authority fades entirely. Objects that drift past this point aren't captured by passing stars so much as simply released, untethered from any particular sun, joining the slow and diffuse population of free-floating bodies that drift between the stars across thousands of light-years. In the most physically precise sense, the outer boundary of the Oort Cloud is the last reach of the sun's gravitational territory. Nothing known to science has ever traveled from inside the solar system, crossed that immense intervening space, passed through the Heliopause, where the solar wind gives way to interstellar plasma, and continued outward through the Oort Cloud and beyond, while remaining, in any meaningful sense, alive. No biological organism, no self-sustaining chemistry, no system capable of carrying information, metabolizing energy, or maintaining structure of any kind. The distances alone would defeat any conceivable biological process. The transit time, measured in centuries or millennia, stretches far beyond the generational span of any known life form under any known metabolic conditions. And beyond the problem of time, there are problems of energy, of radiation, of the deep and absolute hostility of interstellar space. These aren't engineering challenges waiting for more advanced technology. They're expressions of physical law. The question this raises isn't simply a biological one, and it isn't really just about the Oort Cloud. The Oort Cloud defines the gravitational edge of the solar system, the place where the sun's dominion gives way to something far larger and far less sheltering. But it isn't the boundary that the first human-made objects actually crossed. That boundary, the one where physical measurements change abruptly, where plasma temperatures climb by orders of magnitude, where the nature of surrounding space shifts from solar to interstellar, lies much closer. At roughly 120 astronomical units from the Sun, thousands of AU short of the Oort Cloud's inner edge, a different kind of wall exists. One drawn not by gravity, but by electromagnetism and thermodynamic pressure, by the long collision of two vast streams of matter that have been pressing against each other for as long as the solar system has been alive. Understanding that wall, what it's made of, why it burns at temperatures that exceed the surface of the sun, what it shields, and what it means to cross it, requires going back to what the sun actually does to the space around it. The sun doesn't simply shine. It exhales. A continuous supersonic stream of charged particles flows outward from it in every direction, a wind that has never stopped since the solar system formed, streaming outward at hundreds of kilometers per second until it meets something strong enough to push back. What pushes back is the interstellar medium itself. And the boundary between these two forces, invisible to the eye, undetectable without instruments of extraordinary sensitivity, is where the solar system's true functional edge is drawn. It's closer than the Oort Cloud by a factor of 1,000. It's the wall that the Voyager probes have already crossed. And once anything passes through it, moving outward, the mathematics of space travel ensure it will not return. At the farthest reach of what instruments can reliably detect, the question of where the solar system ends is not a settled one. It's a disagreement between different physical frameworks, each measuring a different quality of the sun's reach, and each arriving at a very different number. To a planetary scientist studying the architecture of the Kuiper Belt, the solar system essentially ends at around 50 astronomical units, where the primordial disk of planet-forming material thinned away, and the ordered structure of planets and moons gives way to a sparse, frozen emptiness. To a plasma physicist tracking the behavior of the solar wind, the boundary is the Heliopause, at roughly 120 AU, where electromagnetic pressure, rather than gravity, draws the line. And to a dynamicist working with the most refined models of stellar encounters and gravitational influence, the solar system's edge might lie anywhere from 100,000 to nearly 200,000 astronomical units, depending on how one chooses to define the sun's dominance over the pools of neighboring stars. These aren't small differences. They span 3 orders of magnitude. And they matter, because the choice of definition changes what crossing the boundary actually means. To really understand that boundary, what it's made of, why it burns at temperatures that dwarf the surface of the sun itself, what it holds back, and why crossing it outward means crossing it forever, you have to go back to what the sun actually does to the space around it. The sun doesn't simply shine, it bleeds. It breathes out a continuous supersonic stream of charged particles in every direction, a wind that has never stopped, not once, since the solar system first formed. That wind streams outward at hundreds of kilometers per second, spreading across the dark in all directions, until it finally meets something strong enough to push back. What pushes back is the interstellar medium itself, and the boundary between those two forces, invisible to the eye, undetectable by anything short of the most sophisticated instruments ever sent into deep space, is where the solar system's true functional edge is drawn. It sits closer than the Oort Cloud by a factor of 1,000. It is the wall the Voyager probes have already crossed.
And once anything passes through it, heading outward, the mathematics of space travel ensure it doesn't come back.
At the outer fringe of what instruments can reliably detect, the question of where the solar system ends isn't settled. It's a disagreement between competing physical frameworks, each one measuring a different aspect of the sun's reach, and each one arriving at a very different number.
To a planetary scientist studying orbital patterns in the Kuiper Belt, the solar system essentially ends around 50 astronomical units, where the ancient disk of planet-forming material thinned away, and the ordered world of planets and moons gives way to a sparse, frozen wilderness. To a plasma physicist watching the behavior of the solar wind, the boundary is the Heliopause at roughly 120 AU, where electromagnetic pressure, not gravity, draws the line. And to a dynavicist calculating gravitational reach using refined stellar encounter models, the solar system's edge might fall anywhere from 100,000 AU to nearly 200,000 AU, depending on how you define the sun's dominance over the pull of neighboring stars. These aren't small differences. And to a dynavicist calculating gravitational reach using refined stellar because the definition you choose changes what crossing the boundary actually means. The mathematical tool most often used to measure gravitational dominance is something called the Heliopause equation. It describes the region around a body where its own gravity controls the motion of smaller objects against the tidal pull of a larger one. For the Sun, measured against the Milky Way's collective gravitational field, that calculation yields an enormous number, something on the order of several light years. But the equation assumes idealized conditions that the galaxy's complex, crowded reality doesn't actually permit. In practice, the Sun's effective gravitational territory is far more constrained. Stellar encounters slowly erode the outer Oort Cloud, stripping loosely bound objects away from the Sun's tenuous grip over geological timescales. Galactic tides twist the orbits of distant icy bodies in ways that eventually overpower the Sun's hold. The outer edge of the Oort Cloud isn't a hard wall with a clean mathematical cutoff. It's a smeared, probabilistic gradient, a region where solar ownership becomes statistically uncertain and interstellar influence begins to win more often than it loses. That ambiguity isn't a failure of astrophysics. It reflects something genuinely true about how gravity works.
Gravity doesn't switch off. It diminishes with distance, following the inverse square law, growing weaker but never reaching absolute zero. At 100,000 AU, the Sun still exerts a gravitational pull on surrounding objects. It simply exerts less pull than the combined tidal force of the galaxy's mass distribution. Any boundary you draw is always a zone of competing influences rather than a clean threshold. What changes at the Heliopause is something categorically different. The plasma on one side of that boundary is solar in origin. The plasma on the other side is interstellar. The magnetic field lines trace back to two completely separate sources. The particle populations carry entirely different energy signatures and directional patterns. The Heliopause isn't a gradient. It's a contact discontinuity, a surface where two physically distinct environments press against each other, and neither one can enter the other's territory under normal conditions. Understanding why astrophysicists focus so closely on the Heliopause rather than the gravitational boundary comes down to this. The Heliosphere is, in a practical sense, the solar system's operating environment. The physical conditions that matter for spacecraft, radiation exposure, electromagnetic signal propagation, plasma behavior, are all shaped by conditions inside the heliosphere. A spacecraft operating within the Heliopause moves through plasma produced by the Sun, modulated by the Sun's magnetic field cycle, and partially shielded from the galactic radiation environment by the Sun's outward wind pressure. A spacecraft outside the Heliopause moves through something fundamentally different, an environment that has no connection to the Sun's activity at all. The two are measurably, qualitatively distinct in ways that gravitational calculations alone simply can't capture. Measuring the heliosphere's extent is itself a quiet kind of scientific achievement, because the heliosphere can't be observed from the outside directly. No telescope has yet captured a clean, resolved image of the Sun's heliospheric bubble, the way you might photograph a planetary atmosphere. What scientists have instead are in situ measurements from spacecraft crossing the relevant boundaries, remote sensing observations using ultraviolet spectroscopy, and increasingly refined computer models constrained by those data points. The solar wind follows predictable fluid dynamic equations through most of its journey outward. But the termination shock, where the wind abruptly decelerates below the local speed of sound, wasn't directly detected until Voyager 1 crossed it at 94 astronomical units in 2004. Before that crossing, its location had been estimated from models and indirect measurements of energetic particle populations that behaved differently on either side. What those measurements revealed, cumulatively, is that the heliosphere is neither symmetric nor still. Its nose, the sunward-facing surface pressing into the interstellar wind, is compressed inward by the ram pressure of the interstellar flow. Its tail, stretching away in the opposite direction, extends for thousands of astronomical units downwind, forming an elongated heliotail that has been mapped indirectly through energetic neutral atom imaging by a spacecraft called the Interstellar Boundary Explorer, or IBEX, launched in 2008. IBEX detected a striking ribbon of enhanced energetic neutral atom emission that appeared to trace the boundary between solar and interstellar magnetic field influences, a feature no model had predicted before the mission's first results arrived, one that prompted significant revision of heliospheric models over the years that followed. The shape of the Heliosphere, it turned out, is sensitive not just to the Sun's own output, but to the direction and strength of the interstellar magnetic field pressing against it from outside. The shape of the Heliosphere, it turned out, is sensitive not just to the Sun's own output, but to the direction and strength of the interstellar magnetic field pressing against it from outside. The reason astrophysicists pay such close attention to the Heliopause, rather than to some gravitational boundary far beyond it, is that the Heliosphere is, in a very real sense, the solar system's working environment. The conditions that shape how spacecraft perform, how radiation moves, how electromagnetic signals propagate, all of it is governed by what happens inside that bubble. A spacecraft traveling within the Heliopause moves through plasma the Sun itself produced, plasma that's modulated by the Sun's magnetic cycles, and at least partially sheltered from the harder radiation streaming in from the galaxy beyond. A spacecraft on the other side of that boundary moves through something else entirely, a medium with no connection to the Sun's activity, no memory of it. The two environments are measurably, qualitatively different in ways that no gravitational calculation can describe. Measuring the Heliosphere's extent is, in itself, a quiet kind of achievement, and a difficult one, because the Heliosphere can't be observed from the outside in any direct way. No telescope has ever captured a clean image of the Sun's heliospheric bubble, the way you might photograph a planetary atmosphere from a distance. What scientists have instead are measurements taken in place by spacecraft passing through the boundaries themselves, along with remote sensing through ultraviolet spectroscopy and computer models refined over years of gathered data. The solar wind follows predictable fluid equations through most of its outward journey. But the termination shock, the place where that wind abruptly slows below the local speed of sound, wasn't directly detected until Voyager 1 crossed it in 2004 at 94 astronomical units from the Sun. Before that crossing, its location had only been estimated, inferred from models, and from the behavior of energetic particle populations that moved differently on either side. What those measurements revealed over time and taken together is that the Heliosphere is neither symmetrical nor still. The sunward face, the nose pressing into the oncoming interstellar wind, is compressed inward by the ram pressure of that flow. The opposite side, the tail, stretches away downwind for thousands of astronomical units, forming an elongated heliotail that has been mapped indirectly through energetic neutral atom imaging by a spacecraft called IBEX, the Interstellar Boundary Explorer, launched in 2008. IBEX detected a ribbon of enhanced emission, tracing what appeared to be the boundary between solar and interstellar magnetic influences. No model had predicted it. When the results arrived, they prompted a significant rethinking of how the heliosphere is shaped, and the picture that emerged was one sensitive not just to the sun's output, but to the direction and strength of the interstellar magnetic field pressing in from outside. The Kuiper Belt's outer edge which falls at roughly 50 astronomical units, raises a different kind of question about where the solar system ends. The Kuiper Belt isn't simply a region of space. It's a remnant of the solar system's formation, a fossil record of the conditions that shaped the outer protoplanetary disk while the planets were still assembling. Its outer boundary, sharpened by a gravitational resonance with Neptune that swept the region beyond roughly 48 AU with unusual efficiency, marks the practical limit of the ordered architecture the Sun built during those early years. Beyond that edge, the scattered disk extends further, carrying objects that were gravitationally ejected from the classical belt over billions of years. But even the scattered disk's most distant confirmed members sit well inside the 1,000 AU mark. The space between that population and the inner edge of the Oort Cloud, somewhere around 2,000 AU, is so sparse, so difficult to survey from Earth, that nothing confirmed has been catalogued there yet. Though the object Sedna, found in 2003 with a closest approach of about 76 AU and a farthest point nearing 1,000 AU, hints that a population of intermediate objects may drift through this transition zone, just too few and too far for current instruments to find. This observational gap matters because it means the edge of the solar system, measured by where we can actually detect and track distinct objects, moves outward every time detection technology improves. The boundary is partly a function of what we can see. As survey telescopes become more powerful and surveys more systematic, that apparent outer limit shifts. The Vera C. Rubin Observatory, now in its commissioning phase and preparing to begin its legacy survey of space and time, is expected to find thousands of trans-Neptunian objects in regions that current surveys have barely touched, potentially reshaping the picture of how far the disk's influence truly reaches. The heliospheric boundary is different. It doesn't move when detection improves. It moves when the sun moves, when solar activity rises or falls, when the local pressure of the interstellar medium shifts. It's a dynamic physical surface, but one governed by physics rather than by the limits of our instruments. What comes into view when you look at these different boundaries together is a solar system built from nested layers of influence, each layer governed by its own physics, each with its own characteristic edge. The planet-forming disk has an edge shaped by material density and orbital dynamics. The gravitational domain has an edge shaped by competing stellar masses and the slow pull of galactic tides. The plasma domain, the heliosphere, has an edge shaped by the pressure balance between two supersonic winds meeting in the dark. And at that plasma edge, something genuinely abrupt happens. Not a gradient, not a slow fading, a sharp discontinuity where measurements change suddenly and completely, where the character of space crosses from one condition into another as cleanly as a water's surface separates the air above from the medium below. That discontinuity is what the Voyager probes recorded in real time, what they sent home across more than 23 hours of radio transit, and what transformed the heliospheric boundary from a theoretical construct into something measured, something real. Deep inside the outer heliosheath, where the last traces of solar wind pressure finally yield to the steady inward press of the interstellar medium, The question of life moves from something abstract into something physical, something immediate.
The boundary has been established.
The measurements exist. The plasma wall's temperature, its density, its magnetic structure. These are no longer propositions.
They are numbers, returned across 23 hours of radio silence by machines that carry no passengers, no biology, nothing fragile that might be undone by the conditions they so faithfully record. And the reason they carry no biology is not incidental. It is the whole point. This observational gap shapes how we think about boundaries, because it means the edge of the solar system, defined by where physical objects can actually be detected and tracked, moves further out every time detection technology improves. The boundary is partly a reflection of what we're capable of measuring. As survey telescopes grow more powerful and survey strategies become more thorough, the apparent outer limit of the populated solar system quietly creeps further from the Sun. The Vera C. Rubin Observatory, now finishing its commissioning phase and preparing to begin its legacy survey of space and time, is expected to discover thousands of trans-Neptunian objects in regions that current surveys have barely touched, potentially revealing structure in the outer solar system that reshapes our understanding of where the disk's influence truly fades. The heliospheric boundary, by contrast, doesn't move when detection technology improves. It moves when the Sun moves, when solar activity rises or falls, when the pressure of the local interstellar medium shifts. It's a dynamic physical surface, but one governed by physics rather than the limits of our instruments. What emerges from looking at all these competing definitions is a picture of the solar system as a nested series of influence domains, each with its own governing physics, each with its own characteristic edge. The planet-forming disk has an edge defined by material density and orbital dynamics. The gravitational domain has an edge defined by competing stellar masses and the slow pull of galactic tides. The plasma domain, the heliosphere, has an edge defined by a pressure balance between two supersonic winds. The plasma domain, the heliosphere, has an edge defined by a pressure balance
a gradient,
not a slow statistical fading, a sharp discontinuity where measurements change suddenly and dramatically, where the character of space crosses from one regime into another, as cleanly as the surface of water separates the medium above from the medium below. That discontinuity is what the Voyager probes measured in real time, what they transmitted back across more than 23 hours of radio transit, and what turned the heliospheric boundary from a theoretical construct into a measured, empirical fact. And what those measurements revealed about the wall itself, its temperature, its structure, the forces that sustain it, is when the deeper story begins. Inside the outer heliosheath, where the last whispers of solar wind pressure finally yield to the steady inward press of the interstellar medium, the question of life shifts from the abstract to the physical. And what those measurements revealed about the wall
The
itself,
measurements have been
recorded. The plasma wall's temperature, its density gradient, its magnetic topology, these are no longer theoretical. They are numbers, returned across 23 hours of radio transit by machines that carry no passengers, no biology,
no fragile cellular architecture that might come apart in the conditions they so faithfully document. And the reason they carry no biology is not incidental. It is the point. Life on Earth is not a general phenomenon. It's a highly specific one. Every organism that has ever metabolized, reproduced, or responded to its environment on this planet did so within an extraordinarily narrow corridor of physical conditions. A corridor so narrow that when you measure it against the full range of conditions present in the universe, it looks less like a doorway and more like a hairline crack in a wall. The conditions that allowed that corridor to exist were not random. They were the product of a specific distance from a specific star, a specific planetary mass generating a specific atmospheric pressure, a specific magnetic field quietly deflecting specific radiation, and a specific biochemical solvent, liquid water, that remains liquid only within a temperature range spanning roughly 100 degrees Celsius at standard atmospheric pressure. Step outside that corridor in any single dimension, and the molecular machinery that sustains life simply ceases to function. The temperature of the very local interstellar medium, as measured by Voyager 2's plasma science instrument, falls somewhere between 30,000 and 50,000 Kelvin, which exceeds the surface temperature of the Sun. That number needs some context, because the paradox it contains is genuine and worth sitting with. Kinetic temperature in a plasma is a statistical measure of particle velocity, not a measure of how much heat gets transferred. The interstellar plasma is so extraordinarily diffuse, approximately 0.039 particles per cubic centimeter, compared to roughly 25 quintillion molecules per cubic centimeter in Earth's atmosphere at sea level, that the rate of collision between plasma particles and any passing object is almost negligible. The Voyager probes actually lose more heat through radiative cooling into the surrounding void than they absorb from particle collisions. The 50,000 Kelvin plasma doesn't incinerate them because it has almost nothing to collide with. For a living organism, though, that thermodynamic reprieve isn't really the concern. The concern is the radiation. Galactic cosmic rays are among the most energetic particles in the known universe. They're not electromagnetic radiation in the conventional sense. Not photons, not radio waves, not the kind of ultraviolet light that sunscreen is designed to address. They're fully ionized atomic nuclei, accelerated to velocities approaching the speed of light by supernova shockwaves, pulsar wind nebulae, and the violent magnetic environments surrounding black holes scattered throughout the Milky Way. Roughly 85 to 90% of these particles are simple protons. Between 10 and 13% are helium nuclei, alpha particles. The remaining fraction are heavy, highly charged ions of heavier elements: carbon, oxygen, silicon, iron, collectively called HZE particles for high charge and energy. The HZE fraction is the biologically catastrophic component. The ionization damage a charged particle inflicts on tissue scales with the square of its atomic charge number. An iron nucleus, carrying a charge of 26, delivers damage roughly 676 times more intense than a single proton traveling the same path through tissue. And as these heavy, relativistic nuclei pass through biological material, they don't scatter diffusely. They create narrow, dense columns of ionization, linear damage tracks that tear through DNA strands with a kind of precision and completeness that cellular repair mechanisms simply aren't built to address. Double-strand DNA breaks caused by HZE ions produce clustered damage sites where both strands of the helix are severed simultaneously within a span of just a few nanometers. The cell's repair enzymes work by reading the intact complementary strand to reconstruct whatever's damaged. When both strands are severed in the same region, there's no template left to read. The damage is unrepairable. For a living organism, though, the cold is not the real concern. The radiation is. Galactic cosmic rays are among the most energetic particles anywhere in the known universe. They aren't electromagnetic radiation in the usual sense. Not photons, not radio waves, not the kind of ultraviolet light that sunscreen handles. They are mechanical waves traveling through space-time itself, as fundamental waves as a sound wave through air or ripples on water from a falling stone. They're fully ionized atomic nuclei, accelerated to velocities approaching the speed of light by supernova shockwaves, by pulsar wind nebulae, and by the violent magnetic environments surrounding black holes scattered throughout the Milky Way. They're fully ionized atomic nuclei, accelerated to velocities approaching the speed of light
Between 10
by
and
super
13%
are helium nuclei, alpha particles. The remaining fraction are the heavy, highly charged ions of elements like carbon, oxygen, silicon, and iron. These are collectively called HZE particles for high charge and energy. The HZE fraction is the component that does the most biological damage. The ionization a charged particle causes in living tissue scales with the square of its atomic charge. An iron nucleus, carrying a charge of 26, delivers damage roughly 676 times more intense than a single proton along the same path through tissue. And as these heavy nuclei pass through a living body, they don't scatter diffusely. They carve narrow, dense columns of ionization, tight damage tracks that tear through DNA with a completeness that the cell's own repair systems simply cannot address. The double-strand breaks they cause are clustered, with both strands of the helix severed simultaneously within just a few nanometers of each other. The repair enzymes that normally work to reconstruct damaged DNA rely on reading the intact complementary strand as a template. When both strands are gone at the same location, there's nothing left to read from. The damage can't be repaired. The heliosphere filters out roughly 70% of the galactic cosmic ray flux present in interstellar space. That's not a small thing. It's the difference between Earth's surface radiation dose of around 3 to 6 millisieverts per year and the open interstellar environment, where unmodulated cosmic rays would deliver doses far beyond the threshold for acute radiation syndrome. The Radiation Assessment Detector aboard the Mars Science Laboratory measured the radiation environment during its transit to Mars, still well inside the heliosphere, still partially shielded by the solar wind's magnetic structure, and recorded a dose equivalent of about 1.81 millisieverts per day. A round trip to Mars accumulates roughly 1,070 millisieverts in total. the lethal threshold for acute radiation syndrome, the point at which 50% of exposed people die within 30 days without medical care, sits at around 4,000 millisieverts, delivered in a short period. In the very local interstellar medium, stripped of all heliospheric protection, radiation arrives at rates that would cross that threshold far faster than any transit technology we've ever proposed could bridge the distances involved. And Mawaz, to be precise, sits only 1.5 AU from Earth at its closest approach. The Heliopause is at 120 AU. The radiation exposure scales accordingly, and it doesn't diminish with distance, because the source of galactic cosmic rays isn't local. It's the galaxy itself, arriving from every direction at once, constant and entirely indifferent to the presence of biology. Extremophiles, organisms adapted to the most hostile environments Earth offers, represent the outer edge of what we know about biological tolerance. Tardigrades can survive desiccation, vacuum exposure, and radiation doses exceeding 1,000 Gray in laboratory conditions. Deinonychus radiodurans can reconstruct its own shattered genome after radiation exposures that would destroy any other known organism. These are genuinely remarkable capabilities. They're also completely insufficient for the interstellar medium. A tardigrade in a cryptobiotic state, metabolically suspended, desiccated, still, can endure a vacuum and a sharp burst of radiation. It cannot endure continuous, years-long exposure to an unmodulated galactic cosmic ray flux, while simultaneously being displaced from any energy source capable of sustaining revival. The extremophile tolerance that astonishes researchers in terrestrial labs is measured in hours or days of intense exposure, not decades of continuous bombardment across distances measured in light years. The chemistry doesn't hold. The molecular bonds that preserve biological structure eventually break under sustained irradiation, regardless of how well the organism can repair itself under normal conditions. Temperature in interstellar space adds a separate, compounding constraint. Far from any stellar heat source, the ambient temperature of deep space, the thermodynamic floor set by the cosmic microwave background, is approximately 2.7 Kelvin, or roughly 270 degrees below 0 Celsius. At that temperature, biochemical reactions don't slow down. They stop entirely. Enzymatic function requires molecular flexibility. Proteins need to change shape. Substrates need to diffuse. Reaction intermediates need to migrate through aqueous solution. Water, the universal solvent for Earth-based life, freezes at 273 Kelvin. In interstellar space, it doesn't merely freeze. In a vacuum, it sublimes directly into ice, destroying cellular membrane integrity and crystallizing the intracellular environment in ways that rupture organelles and collapse molecular architecture. No organism built around liquid water chemistry survives that transition. Not one. Not at any scale. Not at any level of extremophile adaptation. Not in any form that 4 billion years of evolution on this planet has ever produced. The distances fold all of this into something that approaches the absolute, even traveling at the velocity of Voyager 1. 17 kilometers per second, a speed that required the gravitational assistance of Jupiter and Saturn and still represents the fastest sustained velocity of any human-made object. The journey from Earth to the Heliopause at 120 AU takes roughly 35 years. The journey to Alpha Centauri, the nearest stellar system at 4.24 light-years, would take approximately 73,000 years. Any biology aboard such a vessel wouldn't be crossing space so much as slowly dissolving into it, molecule by molecule, bond by bond, under continuous radiation that no passive shielding fully resolves and no metabolic repair mechanism can sustain across timescales that long. The physical boundary at the edge of the solar system is real. The plasma wall is real, its temperature measured directly by instruments that crossed a threshold no human eye ever observed. The hydrogen wall is real, its absorption signature detected in Lyman alpha ultraviolet light by the high-resolution spectrograph on the Hubble Space Telescope and confirmed by the ALICE spectrograph on New Horizons. But the deeper boundary, the one that doesn't require traveling 120 AU to encounter, is the one separating the biochemical conditions life requires from the conditions that make up the rest of the universe. That boundary begins at the edge of Earth's magnetosphere. It deepens with every AU traveled outward through the Heliosphere, and at the Heliopause itself, it becomes total. What the Voyager probes crossed into in 2012 and 2018 is not simply a different region of space. It's a region where every physical prerequisite for carbon-based life is absent, all at once, in every measurable dimension, simultaneously. And the question of how any object, living or constructed, might theoretically cross that boundary and survive the attempt remains one of the most daunting engineering problems ever articulated. Far from any star, the temperature of deep space settles near 2.7 Kelvin, roughly 270 degrees below Celsius. At that temperature, the biochemical processes that make up metabolism don't simply slow down. They stop entirely. Enzymatic function depends on molecular flexibility. Proteins need to shift shape. Substrates need to move through solution. Reaction intermediates need to drift through water to find one another. And water, the solvent that Earth's entire biochemistry is built around, freezes at 273 Kelvin. In the interstellar medium, it doesn't even have the chance to freeze properly. It sublimes directly into ice in the vacuum, tearing apart cell membranes, crystallizing the interior of cells, rupturing organelles, and collapsing the molecular structures that life depends on. It sublimes directly into ice in the vacuum, tearing apart cell membranes, not at crystallizing any size, not through any extremophile adaptation, not in any form that 4 billion years of evolution on this planet has ever produced. And then there are the distances. Even traveling at the speed of Voyager 1, 17 kilometers per second, a velocity that required the gravitational pull of both Jupiter and Saturn to achieve, and which remains the fastest any human-made object has ever traveled on a sustained basis, the journey from Earth to the Heliopause at 120 AU took roughly 35 years. The journey to Alpha Centauri, our nearest neighboring star system, at 4.24 light-years away, would take approximately 73,000 years at that same speed.
Nothing biological aboard such a vessel would be traveling through space so much as slowly dissolving into it, molecule by molecule, bond by bond, under the unrelenting pressure of radiation that no passive shielding fully stops, and that no metabolic repair system could sustain across timescales that long.
The plasma wall at the edge of the solar system is real. Its temperature was measured directly by instruments that crossed a boundary no human eye has ever seen. The hydrogen wall is real too, its absorption signature detected in Lyman alpha ultraviolet light by the high-resolution spectrograph aboard the Hubble Space Telescope, and later confirmed by the ALICE spectrograph on New Horizons.
But the deeper wall, the one that doesn't require crossing 120 AU to reach, is the one that separates the biochemical conditions life needs from the conditions that fill the rest of the universe. That wall begins the moment Earth's magnetosphere ends. That wall begins the moment Earth's magnetosphere ends.
What the Voyager probes crossed into in 2012 and 2018 is not simply another region of space. It is a region where every measurable physical prerequisite for carbon-based life is absent, all at once. And the question of how any object, living or constructed, might theoretically cross that boundary and survive constitutes one of the most forbidding engineering problems ever seriously considered. Which leads somewhere unexpected. If the physical conditions necessary for life end at the Heliopause, and perhaps well before it, then how did life arrive on Earth to begin with? And could life survive a crossing in the opposite direction, sealed inside a fragment of rock thrown outward by some ancient, catastrophic collision, drifting slowly through the Heliosphere and eventually beyond the boundary wall itself? This is where panspermia enters, a hypothesis with a deeper and stranger history than most people realize. The word itself comes from the Greek, meaning seeds everywhere. It was given its first formal scientific expression by the Swedish physical chemist Svante Arrhenius in 1903, who proposed that microscopic spores could be carried across interstellar space on the pressure of starlight alone. But the version of panspermia that draws serious scientific attention today was shaped most forcefully by Francis Crick, the co-discoverer of DNA's double helix structure in 1953, and the chemist Leslie Orgel. In 1973, the two published a paper in the journal Icarus proposing what they called directed panspermia, the intentional seeding of life across the galaxy by an advanced civilization. Crick's reasoning wasn't mysticism. It was rooted in probability and physics. The spontaneous emergence of life from non-living chemistry seemed to him so deeply improbable within the time available on the early Earth that the odds improved considerably if life had first arisen somewhere older, somewhere with more favorable conditions, and had then been carried deliberately across the void. Whatever civilization had sent those seeds might long since have disappeared. The cargo, though, would endure. The astronomer Chandra Wickramasinghe, working alongside the cosmologist Fred Hoyle, pressed the idea further still not toward deliberate seeding by intelligence, but towards something more continuous. They proposed a steady rain of organic molecules, and perhaps even viable microorganisms, arriving at Earth via comets. They called this cosmic ancestry. Over decades, Wickramasinghe and Hoyle gathered spectroscopic data suggesting that complex organic signatures observed in interstellar dust clouds matched the absorption profiles of biological material. Their interpretation was contested and remained so. But the central empirical question their work raised, whether microorganisms could physically survive the conditions of interstellar transit, became one of the most serious open questions in astrobiology. And the answer, looked at carefully, is not a simple no. Tardigrades are perhaps the most studied organisms in this context. These microscopic eight-legged animals, formerly classified within the phylum Tardigrada, measure between 0.1 and 1.5 millimeters in length. They live in deep ocean sediment, in high alpine moss, in almost every terrestrial environment on Earth. When conditions become severe, extreme desiccation, radical temperature shifts, vacuum, ionizing radiation, tardigrades enter a state called cryptobiosis. They expel nearly all of their bodily water, pull their limbs inward, and reduce their metabolic activity to roughly 0.01% of normal. In that state, they have survived open exposure to the vacuum of low Earth orbit. They've endured temperatures approaching absolute zero and pressures 6 times greater than those at the deepest point of the ocean. They've absorbed doses of ionizing radiation that would be lethal to a vertebrate many times over, up to 6,000 grays of X-ray exposure in laboratory conditions, which is roughly 6,000 times the dose considered lethal to a human being. In 2019, an Israeli lunar lander called Bereshit crashed on the moon's surface and scattered its payload of dehydrated tardigrades across the lunar regolith. Whether any survived the impact remains unknown. But the fact that the experiment was conducted at all reflects how seriously astrobiologists take the question of biological durability in space. Bacterial endospores are similarly striking. Certain species within the genus Bacillus form endospores, dormant, desiccated structures enclosed in highly resistant outer coats that have been revived from salt crystals estimated to be 250 million years old, though that particular claim remains disputed. In undisputed laboratory conditions, endospores survive ultraviolet radiation, vacuum exposure, and temperature extremes that would destroy active bacteria entirely. The adaptation underlying both tardigrades and endospores is essentially the same, a radical reduction of metabolic activity to a state that is, by most measures, indistinguishable from death, while preserving just enough biochemical architecture to allow revival when conditions eventually improve. These findings aren't in dispute. They form the empirical foundation that keeps panspermia in serious scientific conversation rather than outside it. Tardigrades, those tiny eight-legged animals, barely a millimeter long at their largest, are probably the most studied extremophiles on Earth when it comes to the question of space survival. They live everywhere. Deep ocean sediment, high alpine moss, the thin film of moisture on a piece of bark. When conditions turn hostile, when the water disappears, when the cold becomes severe, when radiation climbs, they do something extraordinary. They pull their limbs inward, expel nearly all the water from their bodies, and slow their metabolism to something like 1/100th% of normal activity. This state is called cryptobiosis, and in it, they become something closer to a dried mineral than a living creature. In this form, tardigrades have survived direct exposure to the vacuum of open space while in low Earth orbit. They've endured temperatures near absolute zero, pressures far exceeding those at the bottom of the deepest ocean trenches, and doses of ionizing radiation that would be lethal to any vertebrate many times over. Laboratory experiments showed that tardigrades in cryptobiosis could withstand up to 6,000 grays of X-ray exposure, roughly 6,000 times the dose that would kill a human being. In 2019, an Israeli lunar lander called Bereshit crashed onto the moon's surface and released its payload of dehydrated tardigrades into the lunar dust. Whether any survived the impact, no one knows. But the fact that they were included at all says something about how seriously astrobiologists take the question of biological endurance in space. Bacterial endospores are similarly resilient. Certain species within the genus Bacillus form these dormant, desiccated structures with highly resistant outer coats, and some have reportedly been revived from salt crystals estimated at 250 million years old, though that particular claim remains contested. What isn't contested is that in controlled laboratory conditions, endospores survive ultraviolet radiation, vacuum exposure, and temperature extremes far beyond what any active bacterium could tolerate. What isn't contested is that in controlled laboratory conditions, endospores survive ultraviolet radiation, vacuum exposure, and temperature extremes far beyond what any active bacterium could tolerate. The underlying adaptation is the same in both tardigrades and endospores, a radical reduction of all metabolic activity down to a state that looks, from the outside, indistinguishable from death, while the biochemical architecture needed for eventual revival stays quietly intact, waiting. These things are real. They form the empirical foundation that makes panspermia worth taking seriously rather than setting aside. And then you apply the actual numbers of interstellar travel, and the picture shifts. A meteorite ejected from Earth by a large impact, carrying viable microorganisms locked in cryptobiotic states, would need to escape Earth's gravitational pull, pass through the Heliosphere, cross the Heliopause, and then move through open interstellar space toward the nearest stellar system. At the velocities that natural impact ejector can achieve, the journey to Alpha Centauri, just 4¼ light-years away, would take on the order of millions of years. Even the most generous estimates place transit times between star systems at somewhere between 1 million and several million years for naturally ejected rocky material. No laboratory experiment has demonstrated cryptobiotic survival anywhere near that scale. The longest credible revivals of dormant biological material involve timescales measured in thousands of years, perhaps hundreds of thousands, and even those results are disputed. Across a million-year transit, The cumulative radiation dose absorbed by any organism embedded in a few centimeters of rock would far exceed the demonstrated tolerance of any known extremophile. The galactic cosmic ray flux that the heliosphere reduces by roughly 70% inside its boundary arrives at full, unmodulated strength beyond it. HZE ions, heavy, relativistic nuclei that tear unrepairable double-strand breaks through DNA, do not relent. They come continuously, at energies that reach through rock. A centimeter of silicate provides some protection, but across millions of years, the accumulated damage to any biological molecule isn't a stress to be endured. It becomes a slow chemical disassembly, and it proceeds toward completion. The hydrogen wall and the plasma barrier at the Heliopause aren't really the problem for panspermia in themselves. A rock moving at interstellar speeds passes through those boundary regions relatively quickly. The boundary isn't the bottleneck. The transit itself is the bottleneck. Millions of years of continuous ionizing radiation. In a vacuum, with no energy input, no metabolic resources, and no possibility of repair. This is the point where panspermia, taken seriously as a physical hypothesis rather than a kind of cosmic poetry, ends up reinforcing the very conclusion it seems to challenge. Life's resilience is real. The cryptobiosis of tardigrades, the radiation resistance of endospores, the survival of organic molecules in the interstellar medium, all of that is genuine, and it is quietly astonishing. But that resilience has been measured against timescales of years or decades, not millions of years. The solar system's boundary isn't only a wall of plasma and magnetic pressure. It's a temporal wall. The time required to move from one stellar system to another, under any mechanism consistent with the physics of natural ejecta, is a duration so vast that no biological structure yet identified on Earth could maintain the molecular integrity needed for revival at the journey's end. Crick understood this. It's precisely why he proposed directed panspermia, rather than the natural kind. A spacecraft with radiation shielding, with deliberate propulsion, carrying perhaps frozen or suspended cargo, sent by a civilization that had solved engineering problems that remain entirely unsolved by any civilization we currently know to exist. His hypothesis acknowledged, quietly, that natural interstellar transfer of viable life is profoundly improbable. The only way around the physics is intelligence and engineering. And intelligence and engineering bring the problem back to the same walls that face any physical attempt to cross the Heliopause and continue outward: the radiation environment, the energy budget, and the deep constraints of the rocket equation governing every kilogram of mass accelerated through space. The solar system's invisible boundary, then, is more than a feature of plasma dynamics and magnetic pressure. The O-ring, flowering petals of starlight, is the outermost veil threaded with the cosmic wind. We see not itself, but the effect it induces in its echoes. It reflects something about biology itself, about the mismatch between the time scales over which life operates and the distances over which the universe is arranged. Panspermia isn't ruled out in principle. But the conditions that would allow it exceed the demonstrated properties of any known organism by several orders of magnitude in the dimension that matters most: time.
The morning of September 5th, 1977, a machine roughly the size of a small car, weighing 825 kilograms, was bolted atop a Titan IIIe rocket at Cape Canaveral and sent up into the Florida sky. It carried no crew, no food, no water, no oxygen. What it carried was a golden record, engraved with greetings in 55 languages, the sound of rain and surf, and a mother's first words to her newborn child, and 116 images of life on Earth. A gesture of quiet optimism from a civilization that understood, even then, that the probe would never come back. Voyager 1 has now been traveling for more than 4 decades. It is the most distant human-made object in existence. And by every meaningful measure of that word, it has barely left. Crick understood this, which is why he proposed directed panspermia rather than the natural kind. A spacecraft with radiation shielding, with deliberate propulsion, with perhaps frozen or suspended cargo, sent by a civilization that had already solved the engineering problems no known civilization has come close to solving. Crick understood this, which is why he proposed directed panspermia rather than the natural kind. A spacecraft with radiation shielding, with deliberate propulsion. The only way around the physics is intelligence and engineering. And those bring the problem right back to the same walls that face any physical attempt to cross the Heliopause and continue onward. The radiation environment, the energy budget, and the tyranny of the rocket equation that governs every kilogram of mass pushed through space. The solar system's invisible boundary, then, is not simply a feature of plasma dynamics and magnetic pressure. It is a statement about the nature of biology itself, about the deep mismatch between the timescales over which life operates and the distances over which the universe is arranged. It is a statement about the nature of biology itself. On the morning of September 5th, 1977, a machine roughly the size of a small car, weighing 825 kilograms, was bolted atop a Titan IIIe rocket at Cape Canaveral and lifted into the Florida sky. It carried no crew. It carried no crew. It carried a golden record engraved with greetings in 55 languages, the sound of rain and surf, and a mother's first words to her newborn child, and 116 images of life on Earth, a quiet gesture of hope from a civilization that understood, even then, that the probe would never return. Voyager 1 has now been traveling for more than 4 decades. It is the most distant human-made object in existence. And by every meaningful measure, it has barely left. Consider what that means in real terms. Voyager 1 travels at roughly 17 kilometers per second, which sounds like a great speed until you apply the mathematics of interstellar distance without softening them. At that velocity, the probe covers about 3.6 astronomical units per year. The Heliopause, the boundary it crossed on August the 25th, 2012, at a distance of 121.6 AU, lies only around 120 AU from the Sun. Alpha Centauri,
the nearest neighboring star system, lies approximately 276,000 AU away. To reach it at its current speed, Voyager 1 would need roughly 73,000 years. The probe will long since have fallen silent by then. Its radioisotope thermoelectric generators, powered by the slow decay of plutonium-238, lose roughly 4 watts of electrical output every year. Mission controllers at NASA's Jet Propulsion Laboratory have been methodically switching off instruments since the early 2000s. A plasma heater here, a gyroscope there, rationing what remains with the careful attention of someone managing very limited resources. Conservative estimates place the last functional transmission sometime in the early 2030s, after which the probe will continue outward in permanent silence, carrying its golden record through a galaxy that may never play it. That silence and the approach of it is worth sitting with for a moment. Every signal Voyager 1 currently sends travels at the speed of light and still takes more than 22 hours to reach Earth. The data arrives at a rate so low that downloading a single image would take hours. The Deep Space Network, a collection of enormous dish antennas in California, Spain, and Australia, some up to 70 meters across, must track the probe continuously just to pull this thin thread of information from the background noise of the universe. What Voyager sends back is not a stream of data. It is a whisper across an immense distance, and even that whisper is fading year by year as the generators cool and the signal weakens with distance. This engineering reality speaks to something that the earlier parts of this journey have examined in thermodynamic and biological terms. The barrier is not only a matter of plasma temperatures and radiation, it is also an intellectual curiosity, a counterpoint to the forces of nature, which teaches humanity how to continue beyond the cosmic distance. It is also, in a deeply practical sense, a communications barrier, an energy barrier, a time barrier. And these compound each other until the combined effect becomes something close to absolute. Voyager 1 is not a demonstration of interstellar reach. It is a scientific odyssey threading needles between stars to weave a tapestry of our human existence. It is a demonstration of interstellar proximity, a proof that humanity can arrive at the edge of its own electromagnetic domain, and no further, not with the tools that exist now, or any tools foreseeable within the near future. The probe carries nothing alive. That was not an oversight. The engineers who designed the Voyager missions understood the radiation environment of the outer heliosphere well enough to know that no biological cargo could survive even the transit to the termination shock, let alone the crossing of the Heliopause itself. The golden record is not a container of biology. It is a container of information, encoded in a physical medium chosen specifically because properly inscribed matter can endure environments that no living thing can. That choice was deliberate. It was an acknowledgement, built into the very architecture of the mission, that living things and the edge of the solar system are incompatible destinations. And what Voyager's instruments revealed when it crossed the Heliopause in 2012 confirmed the wisdom of that decision in ways that prior models hadn't fully anticipated.
The plasma wave subsystem, detected in October 2013, electron plasma oscillations corresponding to a local electron density of 0.055 particles per cubic centimeter, a rise of more than 20-fold from the typical outer heliosphere density of 0.002 particles per cubic centimeter. The magnetic field measured outside the heliopause ran nearly parallel to the Sun's own magnetic field, a result so unexpected that it prompted years of theoretical debate before Voyager 2's crossing in November 2018 confirmed the alignment wasn't anomalous at all, but structural. The heliosphere distorting the local interstellar magnetic architecture across a vast surrounding volume. These were not measurements a biological payload could have survived to witness. They were measurements that a hardened, radiation-tested machine survived, barely, at the cost of its plasma instrument, which had failed 32 years before the very crossing it was partly built to document. There's something worth sitting with in what all of this actually means. The wall that earlier parts of this story described in terms of plasma and radiation and biology, it isn't only those things. It's also a communications barrier, an energy barrier, a time barrier. And these don't simply add to one another. They compound quietly until the combined weight of them becomes something close to absolute. Voyager 1 is not proof that humanity can reach the stars. It's proof that humanity can reach the edge of its own electromagnetic neighborhood and no further. Not with the tools we have now, and not with any tools that sit within a foreseeable horizon. Not with the tools we have now, and not with any tools that sit within oversight. The engineers who built the Voyager missions understood the radiation environment of the outer heliosphere well enough to know that no biological cargo could survive even the approach to the termination shock, let alone the Heliopause crossing itself. The golden record isn't a container of life. It's a container of information, encoded in physical matter precisely because matter, properly inscribed, can endure environments that no living thing ever could. It's a container of information, encoded in physical matter, woven into the mission's very design, that living things and the edge of the solar system are simply not compatible destinations. The data Voyager sent back after crossing the Heliopause in 2012 confirmed the wisdom of that decision in ways no prior model had fully anticipated. In October 2013, the probe's plasma wave subsystem detected electron plasma oscillations pointing to a local electron density of around 0.055 particles per cubic centimeter, more than 20 times denser than the typical outer heliosphere. The magnetic field measured beyond the heliopause ran nearly parallel to the Sun's own field, a result so unexpected that it sparked years of theoretical debate. It wasn't until Voyager 2 made its own crossing in November 2018 that the picture clarified. The alignment wasn't an anomaly. It was structural. The heliosphere reshapes the local interstellar magnetic architecture across an enormous surrounding volume. These measurements came back to us because a hardened, radiation-tested machine survived long enough to take them. Barely. Its plasma instrument had failed 32 years before the very crossing it was partly built to document.
The scale of what lies beyond becomes clearer when you consider not the Heliopause itself, but the Oort Cloud, the vast, diffuse reservoir of icy bodies that begins somewhere between 2,000 and 5,000 astronomical units from the Sun.
That inner edge sits anywhere from 17 to 40 times farther out than the Heliopause. At Voyager 1's current velocity of 17 kilometers per second, reaching it would take roughly 300 years. No spacecraft in development is built for a 300-year mission. No power system ever flown in space could sustain one for 3 centuries. The RTGs aboard Voyager are measured in decades. And beyond the question of power, there's the question of communication. At 2,000 astronomical units, a radio signal traveling at the speed of light takes about 11.5 days to reach Earth. At 5,000 AU, that one-way delay stretches past 28 days. The idea of real-time mission control disappears entirely. Any spacecraft operating at those distances would have to function as a fully autonomous system, navigating, deciding, existing without any possibility of guidance from the civilization that sent it out. None of this is guesswork. These numbers follow directly from the same physics that governed Voyager, the same orbital mechanics, the same signal propagation, the same power decay curves that NASA engineers have always worked with. These findings are far from invention, but mere confirmation of the scientific universe. The arithmetic isn't discouraging in the way a difficult engineering problem is discouraging. It's discouraging in the way a fundamental constraint is discouraging. The way the speed of light is discouraging. Not because engineers haven't been clever enough, but because the universe simply doesn't negotiate. Stripped of everything sentimental, what Voyager 1 represents is the absolute limit of 20th century human engineering applied to the question of how far we can reach. It's a machine that outlived every expectation, returned data of real and lasting scientific value, and crossed a boundary no human-made object had ever crossed before. It did all of this while carrying no biological passengers, offering no possibility of a return journey, and drifting steadily toward the permanent silence that waits for every machine whose power is finite and whose destination has no end. It isn't a herald of humanity's arrival at some galactic threshold. It's a measurement of the distance still remaining. The wall, then, isn't simply the Heliopause as a plasma boundary. It isn't only the hydrogen wall as a slow accumulation of charged gas. It's the layered, compounding reality that the energy needed to reach the boundary exceeds what any surviving vehicle can carry, that the time required exceeds the lifespan of any power source yet made, and that the radiation beyond the boundary exceeds what any known organism could endure. Voyager crossed the Heliopause because it needed no propulsion to do so. The gravity assists had already given it the velocity for permanent solar escape, and it only had to coast. It survived because it carries no biology. It can't return because the rocket equation won't allow it. Each of these facts leans on the others. Together, they don't describe a single wall. They describe a wall built from physics itself, layered, redundant,
such that removing any one layer simply reveals another one sitting quietly behind it.
And so the golden record drifts on, out through the very local interstellar medium, engraved with the sound of rain that hasn't fallen on Earth for decades now, with a mother's voice speaking to a child who is already old. With music that was centuries old when it was chosen, it will outlast the civilization that made it. It will outlast the star that warmed the world where that civilization slowly came into being. And in all likelihood, it will do all of this without ever being heard, without ever reaching anything capable of listening. A quiet monument to how far human ambition has always been willing to reach, and to the extraordinary precision with which the universe has arranged its distances to remain just beyond it. What Voyager 1 represents, when you set sentiment aside, is the furthest reach of 20th century human engineering directed toward a single purpose: getting as close to interstellar space as anything we have ever built. It's a machine that has outlived every expectation placed on it, returned data of genuine scientific value, and crossed a boundary no human-made object had ever reached before. And it did all of this, carrying no passengers, with no possibility of return, drifting year by year toward the permanent silence that waits for every machine whose power is finite and whose destination has no end. Voyager isn't a herald of humanity arriving at some galactic threshold. It's a measurement of how far away that threshold still is. The wall, then, is not simply the Heliopause as a shift in plasma. It's not only the hydrogen wall as a slow accumulation of charged and neutral gas. It's the layered reality that the energy needed to reach the boundary exceeds what any vehicle could carry and still survive the journey. That the time required outlasts any power system we've yet built, and that the radiation waiting beyond that boundary exceeds what any known organism could endure. Voyager crossed the Heliopause because it didn't need propulsion to do so. Gravity assists had already given it more than enough velocity to escape the sun permanently, and from there it simply coasted. Gravity assists had already given it more than enough velocity to escape the sun permanently, because the physics of rocketry won't allow it. Each of these facts reinforces the others. Together, they don't describe a single wall, so much as a wall built from physics itself, layer after layer, so that moving through one layer only reveals the next one, waiting quietly behind it. The golden record drifts outward through the very local interstellar medium, carrying with it the sound of rain that hasn't fallen on Earth in decades, a mother's voice speaking to a child who is now old, music that was already centuries deep when it was chosen. It will outlast the civilization that made it. It will outlast the star that warmed the world where that civilization grew. And it will do all of this, in all probability, without ever being heard by anything capable of listening. A quiet monument to the reach of human ambition, and to how precisely the universe has arranged its distances to exceed it. The space between star systems, inside the slow gravitational architecture of the Milky Way, is not empty in the way that word suggests. It's empty of planets, empty of atmosphere,
empty of the kind of continuous magnetic shelter that makes biological life possible. But it isn't empty of motion or force. The galactic tide moves across the disk of the galaxy as an immense, slow gravitational gradient, pressing on any object loosely enough bound to its parent star to feel the difference in pull between one side of its orbit and the other. This is what shapes the Oort Cloud's outermost edge and defines how permeable that edge really is. Objects at the very fringe of the Sun's gravitational reach, cometary bodies 100,000 AU out or further, aren't anchored in any secure sense. They hang in a kind of gravitational negotiation between the Sun and the galaxy itself, and that negotiation doesn't always resolve in the Sun's favor. Passing stars disturb this balance, quietly and constantly. Every few million years, a neighboring star system drifts close enough to the outer Oort Cloud to nudge the orbits of cometary bodies. The nudge is gentle by any earthly measure, a small adjustment to the velocity of an object that was barely held in place to begin with. But small adjustments to barely bound objects have large consequences. Some comets are pushed inward, developing long, stretched orbits that eventually carry them deep into the inner solar system. Others are pushed outward, past the threshold of escape, and they leave the solar system entirely, drifting out into interstellar space as wandering objects. The Oort Cloud isn't a sealed container. It leaks, slowly and continuously, releasing its most loosely held members into the wider galaxy. And this leakage is the same mechanism that makes the idea of traveling between star systems, for any object, living or mechanical, not merely difficult, but structurally strange as a concept. Consider what the journey from our solar system to Alpha Centauri, 4.24 light-years away, would actually mean. You'd need to pass through the outer Oort Cloud, then through a long region of interstellar space that belongs to neither star, then through whatever cometary reservoir surrounds Alpha Centauri, and finally down into the deep gravitational pull of the star itself. At no point along that path is there a clean handoff. Gravitational dominion doesn't transfer smoothly. It dissolves into a long, ambiguous middle region, where something is too far from the Sun to be bound to it, and too far from Alpha Centauri to be bound to that either. In astrodynamics, this is understood through the concept of the Heliopause, the region within which a body's own gravity dominates over the tidal pull of something more distant. The Sun's Heliopause, measured against the galactic center, extends somewhere between 125,000 and 230,000 AU, depending on the model. Alpha Centauri's is similar in scale. Between the two, any object traveling at a speed achievable by anything we could build or imagine building in the near future would spend thousands of years in a gravitational void, not falling toward either star, not returning to either system, simply coasting through a place where no stable orbit exists and no gravitational help is available. For anything biological attempting that crossing, even something dormant, sealed inside rock, carried along as part of a naturally ejected fragment, the difficulty doesn't end at leaving the solar system. It would enter that interstellar void and remain there for millions of years, exposed to unshielded galactic cosmic rays with no prospect of being gravitationally captured by the destination, unless the approach angle was almost impossibly precise. The chances of a random piece of interstellar ejecta arriving at exactly the right velocity and angle to be drawn into orbit around a target star, rather than simply flying past it, are extraordinarily small. Capture without propulsion requires shedding kinetic energy somehow, through atmospheric drag, or a close encounter with a large orbiting body, or a perfectly timed interaction with something like a giant planet. None of those can be arranged in advance by a rock tumbling silently through interstellar space. There's a quietness to this idea, if you let it settle. The space between star systems isn't simply large, it's structured in a way that resists crossing, not through any active force, but through the slow, patient mathematics of gravity itself. Think about what it would actually mean to travel from the Sun's gravitational reach to that of the nearest star system, Alpha Centauri, sitting roughly 4¼ light-years away. You'd move outward through the Oort Cloud, then into a long stretch of interstellar space that belongs to neither star, a kind of gravitational no-man's land, and then, eventually, into the outermost edges of Alpha Centauri's own distant reservoir of ancient ice and rock, and finally down toward the star itself. At no point along that journey does one star's gravity simply hand you off to the other. There's no smooth transition, no clean boundary where one influence ends and the other begins. What there is, instead, is a long and ambiguous middle region, a place where you've drifted too far from the Sun to remain bound to it, and still too far from Alpha Centauri to be drawn toward it. You float, untethered, between two worlds that neither claim you. In orbital mechanics, this is described through something called the Heliopause, the region around a celestial body where its gravity is the dominant organizing force, rather than the pull of something larger and more distant. The Sun's Heliopause, measured against the gravitational influence of the galaxy itself, stretches somewhere between 125,000 and 230,000 astronomical units, depending on how you model it. Beyond that, the slow tide of the galaxy takes over. Alpha Centauri has its own Heliopause of similar scale. And between the two, any object traveling at speeds we could realistically achieve, even with propulsion technologies well beyond what we have now, would spend thousands of years simply coasting. Not falling toward anything, not returning to anything, moving through a region where no stable orbit exists, and gravity offers no assistance in any direction. For a biological traveler, this matters deeply. An organism making that crossing, even a dormant one, sealed inside a fragment of rock carried outward by some ancient planetary collision, wouldn't simply arrive at Alpha Centauri once it left the solar system. It would enter the void and remain there, perhaps for millions of years, exposed to the full, unshielded flux of galactic cosmic radiation. And even then, reaching the destination wouldn't be guaranteed. Gravitational capture, actually being drawn into orbit around another star, requires arriving at exactly the right speed from exactly the right direction. Without some mechanism to shed kinetic energy, A passing object doesn't settle into orbit. It flies through on a curved path and continues outward. The geometry required for natural capture is extraordinarily precise, and it can't be arranged by a rock tumbling silently through interstellar space. Computer simulations of early planetary formation have made this picture clearer. When researchers model the gravitational dynamics of young solar systems, they find that the vast majority of objects ejected during that chaotic early period leave on hyperbolic trajectories, unbound paths that carry them outward indefinitely, never interacting meaningfully with another star. The fraction that achieves genuine gravitational capture by a second system is, in most of these simulations, effectively zero on any individual basis over timescales we might consider reasonable. The lengthy weight of the scientific words carry the emotion. Inflections are subtle and sophisticated, avoiding any sudden dramatic spikes in energy. The interstellar object known as Oumuamua offered the first direct look at this process in reverse. Detected in October of 2017, it was clearly something that had come from outside. Its trajectory, its speed, the way it moved through the inner solar system and out again, all pointed to an origin elsewhere in the galaxy. But Oumuamua didn't settle here. It passed through at roughly 26 kilometers per second relative to the Sun, moving far too fast for solar gravity to hold it. It arrived from the interstellar medium. It returned to the interstellar medium. The solar system was not a destination for it, only a brief gravitational encounter that bent its path slightly, without changing its fundamental nature as an unbound, wandering object. The same physics applies in the other direction. Voyager 1 and Voyager 2 are both on hyperbolic trajectories now, moving outward and away on paths that will carry them into interstellar space indefinitely. If either of them ever drifts close to another star system, and that would take an enormous span of time, they wouldn't slip quietly into orbit there. They'd feel the edge of that system's gravity, be gently deflected, and continue on. The galaxy isn't organized like a collection of rooms with open doorways between them. It's a landscape of deep gravitational wells, separated by vast stretches of dynamic emptiness, and moving from one well to another requires either enormous energy or a natural coincidence so precise it approaches the impossible. And so this is the invisible wall that orbital mechanics builds. The Heliopause, the hydrogen wall, the unrelenting pressure of cosmic radiation. Those are the physical textures of the boundary, the things you'd encounter if you moved through it. But beneath all of that is something more fundamental, a mathematical reality. The space between stars isn't just large, it's dynamically hostile to the kind of gradual, staged journey that life would require. Surviving the crossing is only part of the problem. Arriving somewhere is the other. And arrival, in any gravitational sense, means achieving a stable orbit, or a gentle descent onto solid ground, within a system that has no reason to catch you and no mechanism to slow you down. The Oort Cloud itself offers a quiet illustration of just how difficult this is. Objects that have spent 4 billion years moving at the slow, barely bound velocities of the outer solar system shaped and held by the sun's gravity across the entire age of the planets, are still lost to the galaxy at a steady, gentle rate, nudged free by the gravitational whisper of passing stars and the long, slow tide of the Milky Way. If bodies with that much history, that much orbital shaping, can still be stripped away by such subtle perturbations, then the idea of an inbound interstellar object achieving stable capture, arriving from the void, slowing down, settling in, carries a weight of improbability that's difficult to overstate. The galaxy doesn't offer pathways between systems. What it offers is the tide and the void and the slow arithmetic of gravitational drift, quietly redistributing objects across an immense and indifferent commons, without ever truly delivering them anywhere new. The same physics applies to any object trying to make that journey in reverse. Something leaving the solar system on a hyperbolic trajectory, as Voyager 1 is doing, as Voyager 2 is doing, as any probe, given enough velocity to escape, will do, won't simply become gravitationally bound to the next star system it drifts toward. It will interact briefly, distantly, with that system's gravitational field, be slightly deflected or slowed, and then continue on. The galaxy isn't organized into neat compartments with permeable walls that objects pass through. It's organized into gravitational wells, separated by vast stretches of dynamic emptiness, and moving between those wells requires either an enormous expenditure of energy or the extraordinarily unlikely alignment of a natural capture event. This is the layer of the invisible wall that orbital mechanics builds. The plasma of the Heliopause, the hydrogen wall, the galactic cosmic ray flux, these are the physical texture of the boundary. But beneath all of that lies something more fundamental. The simple mathematical reality that the space between star systems isn't just large, it's dynamically hostile to the kind of gradual, staged crossing that biology would need. A living organism doesn't just need to survive the journey. It needs to actually arrive somewhere. And arrival, in the gravitational sense, means achieving a stable orbit or a soft landing within the destination system. From an interstellar approach, without propulsion, without a gravitational brake already in place, without a giant planet in precisely the right position at precisely the right moment. That isn't merely improbable. The Oort Cloud's own behavior shows the scale of this challenge. Objects that have spent billions of years in the outer solar system, drifting at the slow, cold velocities of bodies barely held by the sun, are still lost to the galaxy at a steady rate, because passing stars and the gentle pull of the galactic tide make small, incremental adjustments to orbits that were already marginal. If bodies shaped by the solar system's gravity across 4 billion years can be stripped away by those quiet tidal nudges, then the prospect of an inbound interstellar object achieving stable capture, without propulsion, without billions of years of orbital history, dissolves under the weight of its own unlikelihood. The galaxy doesn't offer on-ramps between star systems. It offers the void, the tide, and the slow arithmetic of gravitational perturbation that shuffles objects across interstellar space without ever delivering them intact to a new home. The wall, understood this way, reaches beyond plasma and radiation and time. It reaches into the geometric logic of how gravitational systems are arranged and how they interact, or rather, how completely they fail to interact in any way that would allow a smooth biological passage between them. The invisible wall isn't only where the sun's magnetic field ends and the galaxy's begins. It is a zone of turbulence, where charged particles from the sun's wind are suddenly stopped, and the antiquities of the cosmic are entering. It's where gravitational coherence itself ends, and where the assumption that a departure marks the beginning of an arrival shows itself to be the deepest misconception of all. Leaving isn't the hard part. The hard part is that leaving and arriving are not the same journey. Between them lies a structure of orbital mechanics that doesn't treat biological transit as difficult. It treats it as something the physics simply doesn't produce. Deep in the interstellar void between the Sun and Alpha Centauri, where no magnetic field organizes the charged particles and no solar wind mediates the silence, the universe reveals something about itself. The distance between those two stellar neighborhoods, 4.24 light-years, roughly 268,000 astronomical units, isn't simply a large number. It's a statement about the geometry of existence itself, about how matter that can think and wonder and calculate has been distributed across a cosmos that was under no obligation to place anything close to anything else. Consider what that distance means in terms of time. Voyager 1, the fastest object humanity has ever placed in space, using the accumulated momentum of 4 planetary gravity assists, is moving right now at approximately 17 kilometers per second. At that speed, fast enough to carry a traveler from Earth to the Moon in under 7 hours, the probe still needs 73,000 years to reach the nearest star. 73,000 years. That span is longer than the entire recorded history of anatomically modern human thought. It holds within it the collapse and rise of ice ages, the migration of our ancestors out of Africa, the extinction of the Neanderthals, the invention of writing, the construction and ruin of every civilization in the archaeological record, and the whole of everything human beings have ever thought, spoken, built, or remembered. Voyager 1 will travel for a duration equal to all of that, and then repeat it more than 1,000 times over before it drifts into the gravitational neighborhood of another star. No biochemistry survives on those timescales. This isn't a question of how tough an organism is, or how much evolutionary ingenuity life can bring to bear. It's a question of molecular physics. The most radiation-resistant organisms we know of on Earth, Deinococcus radiodurans, capable of surviving doses of up to 1.5 million rads and reassembling its shattered genome within hours, exist inside a very specific context: liquid water, enzymatic repair machinery, a continuous metabolic budget. Remove the water. Remove the energy source. Expose the cellular architecture to the unmodulated cosmic ray flux of interstellar space. where high-energy iron and nickel nuclei carry enough ionizing force to damage a column of tissue in a single pass, and where that damage accumulates across centuries, then millennia, then millions of years. The question is no longer whether the organism can repair the damage. It becomes whether the molecules that carry the instructions for repair retain any meaningful fidelity after 10 million years of that kind of bombardment. They don't. The mathematics of nucleotide degradation under continuous high-energy particle exposure guarantees molecular dissolution long before any biological payload could approach another star through natural drift. The universe doesn't forbid life from attempting this crossing. It simply arranges the attempt so that whatever arrives, if anything arrives at all, is chemistry rather than biology. Sterilized carbon compounds, amino acid fragments, the residue of what was once a replicating system, reduced to its constituent pieces by the patient, indifferent arithmetic of ionization and time. The invisible wall doesn't need to be crossed for the wall to have already won. It wins by attrition, by scale, by the quiet geological enormity of what an interstellar crossing actually demands from matter organized enough to be called alive. Think for a moment about what that distance actually means in terms of time. Voyager 1, the fastest object humanity has ever sent outward, carrying the accumulated momentum of 4 planetary gravity assists, is moving right now at roughly 17 kilometers per second. That's fast enough to carry something from Earth to the Moon in under 7 hours. And yet, at that speed, the probe would need 73,000 years to reach the nearest star. And yet, at that speed, the probe would need is longer than the entire arc of modern human thought. It holds within it the collapse and rise of ice ages, the long migrations of our ancestors out of Africa, the disappearance of the Neanderthals, the slow invention of writing, the building and crumbling of every civilization that archaeology has ever found, everything human beings have ever thought, spoken, made, or remembered. Voyager would travel that entire span, and then repeat it more than 1,000 times over, before it so much as drifted into the gravitational neighborhood of another star. No biochemistry survives on timescales like that. Not because life isn't tough enough or clever enough in its evolution, but because the problem isn't biological, it's molecular physics. The most radiation-resistant organism we know of, Deinococcus radiodurans, can absorb doses of up to 1.5 million rads and reassemble its shattered genome within hours. And yet even that organism exists inside a very specific context: liquid water, enzymatic repair machinery, a continuous supply of metabolic energy. Take the water away. Take the energy source away. Expose the cellular structure to the unmodulated galactic cosmic ray flux of interstellar space, where HZE ions, relativistic iron and nickel nuclei, can ionize an entire column of tissue in a single pass, and let that damage accumulate across centuries, then millennia, then millions of years. The question is no longer whether the organism can repair itself. The question is whether the molecules carrying the repair instructions still hold enough integrity after 10 million years of continuous bombardment to mean anything at all. They don't. The mathematics of nucleotide degradation under that kind of particle exposure ensures molecular dissolution long before any biological payload could drift naturally to another star. The universe doesn't forbid life from attempting that journey. It simply ensures that whatever arrives, if anything arrives at all, is chemistry rather than biology. Sterilized carbon compounds. It simply ensures that whatever arrives...
The residue of what was once a replicating system, worn down to its constituent elements by the slow, patient arithmetic of ionization and time. The wall doesn't need to be crossed to win. It wins by attrition, by scale, by the sheer geological enormity of what an interstellar crossing actually demands from matter organized enough to be called alive. And here is where the deeper meaning of the heliosphere's boundary begins to settle in. The Heliopause isn't simply a plasma discontinuity sitting out at 120 astronomical units. It's the outermost expression of a gravitational and electromagnetic envelope that makes the inner solar system habitable in the first place. Without it, the galactic cosmic ray flux reaching Earth's surface would increase catastrophically. The atmosphere wouldn't be enough. The magnetosphere wouldn't be enough. The roughly 70% of relativistic particle radiation that the heliosphere currently absorbs, deflects, and softens, all of that would arrive unimpeded. The steady radiation environment at the surface would shift from something compatible with complex multicellular life to something compatible only with organisms living deep in the rock, if anything at all. The wall protects inward just as absolutely as it isolates outward. It is, at the same time, the reason Earth stays biologically alive and the reason Earth stays biologically alone. What comes into view through all of this is a picture of planetary systems as islands, gravitational and electromagnetic islands, not merely separated by distance, but enclosed within their own stellar influence in a way that makes each one its own self-contained world. Inside the heliosphere, the physics follows the sun's rules. The sun's magnetic field, the sun's wind pressure, the sun's shaping of particle fluxes. Outside the Heliopause, the physics follows the galaxy's rules. The interstellar medium's electron density, the cosmic ray spectrum shaped by supernovae and pulsar wind nebulae thousands of light years away, the neutral hydrogen drifting through at 26 kilometers per second, indifferent to anything any individual star might be doing. These two regimes don't negotiate. They balance at a pressure discontinuity roughly 1.5 astronomical units thick. And beyond that line, the sun's reach simply ends. This is why a biological crossing, in either direction, outbound from the solar system or inbound from another, doesn't just require the right organism, it requires the right physics. And the physics is systematically wrong for it. An organism leaving the solar system moves from a magnetically sheltered environment, shaped over billions of years of co-evolution between life and planetary protection,
directly into an environment that has never been hospitable to anything resembling Earth life. An organism arriving from another star faces the same problem in reverse, carrying with it the accumulated damage of geological time spent in transit through precisely that hostile environment, and then still needing to cross inbound through the Heliopause, pushing against the outward ram pressure of the solar wind, through a boundary that deflects interstellar plasma and filters interstellar gas with quiet, relentless efficiency. And then there is the hydrogen wall itself, that vast accumulation of decelerated neutral hydrogen piling up just outside the Heliopause through resonant charge exchange. It's a real structure. Confirmed by Lyman alpha ultraviolet spectroscopy from the Hubble Space Telescope, and independently measured by the ALICE ultraviolet spectrograph aboard New Horizons, which detected a persistent excess brightness of roughly 40 Rayeys that can't be explained by the expected decay of local interplanetary hydrogen. The wall blankets the solar system's outermost edge with dense neutral gas that interacts with charged particles and electromagnetic radiation in ways that further complicate any transit scenario. The solar system is enclosed, sealed from without by layered, overlapping physical barriers, each operating on a different scale and through a different mechanism, but all of them arriving at the same quiet conclusion: isolation. When Jeff Linsky and Brian Wood analyzed Lyman alpha absorption in the direction of Alpha Centauri, they weren't simply finding a structure around our own sun. They were recognizing something that other stars possess as well: astrospheric hydrogen walls surrounding stellar systems across the galaxy, each one marking the place where that star's wind finally gives way to interstellar space. Every star with a significant stellar wind generates its own bubble, its own termination shock, its own heliopause, its own hydrogen wall. The galaxy is not an open sea through which life might drift freely from one shore to another. It's an archipelago of sealed, pressurized envelopes, each one inflated by a different star, each one separated from its neighbors by tens of thousands of astronomical units of cold vacuum, where galactic cosmic rays move without impediment, and neutral hydrogen flows at velocities shaped by the galaxy's own slow bulk motion, paying no attention to any of the small, warm lights scattered through it. And so we find ourselves here, at the quiet edge of everything we've ever known. Because crossing between the stars, whether something leaves this solar system or arrives from another, requires more than just the right organism. It requires the right physics. And the physics, in every direction we look, works against it. Something leaving the solar system would pass out of a magnetically sheltered environment, one shaped across billions of years of slow, quiet coevolution between life and the layers of protection surrounding this planet, and into a space that has never once been hospitable to anything resembling Earth life. Even the hydrogen wall, that vast, slow accumulation of neutral hydrogen that piles up just outside the Heliopause, is a real structure, not a theory. The Hubble Space Telescope confirmed it through Lyman alpha ultraviolet spectroscopy, and the ALICE spectrograph aboard New Horizons measured a persistent excess brightness of roughly 40 Raylys that simply cannot be explained by the ordinary decay of local interplanetary hydrogen. It is there, a dense compression of neutral gas at the outer boundary, interacting with charged particles and electromagnetic radiation in ways that complicate any transit scenario you might imagine. The solar system is enclosed by layered, overlapping physical barriers, each one operating through a different mechanism, each one arriving at the same result: isolation. When Jeff Linsky and Brian Wood carried out their spectroscopic analysis of Lyman alpha absorption toward Alpha Centauri, they weren't only confirming a structure around our own sun, they were recognizing a feature that belongs to other stars as well: astrospheric hydrogen walls surrounding stellar systems across the galaxy, each one marking the place where a star's wind finally gives way to the interstellar medium. Every star with a significant stellar wind generates its own bubble, its own termination shock, its own heliopause, its own wall. The galaxy is not a continuous open medium through which life might drift freely from one star to the next. It is an archipelago of sealed, pressurized envelopes, each one inflated by a different star, each one separated from its neighbors by tens of thousands of astronomical units of open space, where galactic cosmic rays move without resistance, and neutral hydrogen drifts at velocities shaped by the galaxy's own slow turning, far beyond any local stellar influence. Between those envelopes lies a crossing that has never been made alive. Between them lie timescales that exceed biochemical stability by factors of thousands. Between them moves radiation that dismantles molecular information faster than any known repair mechanism can rebuild it. And between them sits the rocket equation, its exponential demand unyielding, requiring a mass ratio approaching 2,000 for every kilogram of payload attempting to reverse a hyperbolic interstellar trajectory. The conservation of momentum holds. It has always held. It will not be negotiated with. Voyager 1 is out there now, moving silently through the very local interstellar medium at 17 kilometers per second. Its plutonium-238 generators lose roughly 4 watts of power each year. Its transmitter still sends signals home. Signals that take more than 23 hours to reach the deep space network antennas on Earth. In perhaps another decade, the power will fall below the threshold needed to run any scientific instrument. The probe will go quiet, and then it will continue moving outward for billions of years, carrying the golden record, its cargo of mathematics and music, and the image of a human hand raised in greeting, through a medium that has never answered, towards stars it will never reach on any timescale that means anything to the civilization that built it. The wall holds. The wall holds, not because the universe is hostile, though it is, in every measurable dimension beyond the Heliopause, but because the wall isn't a barrier in the conventional sense. It isn't a surface to be breached with enough force, or enough technology, or enough will. It is the architecture of physical reality as it applies to the relationship between gravity wells and stellar winds, between interstellar space and time and the fragile chemistry that constitutes life. It is the sum of every constraint the cosmos has placed on the movement of organized matter between the islands of stellar light scattered across the galaxy. Nothing alive has crossed it. And the physics doesn't make this a tragedy. The physics makes it a fact, as settled and as permanent as the inverse square law, as the rocket equation, as the speed at which a Lyman alpha photon travels from the surface of the sun to the hydrogen wall and back, in a universe that has been running its calculations for 13.8 billion years and has arrived again and again at the same quiet answer. The wall stands. The void holds. And the nearest star waits, 4.24 light years away, as it has always waited. Unreachable, not through any failure of imagination, but through the patient, absolute mathematics of the cosmos itself. You rest in that understanding now. Let it settle, slowly, like everything else in the dark between the stars. There is nothing left to reach for tonight. Only the vast, unhurried quiet of a universe at rest. Only the vast, unhurried quiet of a universe at rest. But beneath all of that lies something more fundamental. The simple mathematical reality that the space between star systems isn't just large, it's dynamically hostile to the kind of gradual, staged crossing that biology would need. A living organism doesn't just need to survive the journey. A living organism doesn't just need to survive the hard part is that leaving and arriving are not the same journey. Between them lies a structure of orbital mechanics that doesn't treat biological transit as difficult. It treats it as something the physics simply doesn't produce. Deep in the interstellar void between the Sun and Alpha Centauri, where no magnetic field organizes the charged particles and no solar wind mediates the silence, the universe reveals something about itself. The distance between those two stellar neighborhoods, 4.24 light-years, roughly 268,000 astronomical units, isn't simply a large number. About how matter that can think and wonder and calculate has been distributed across a cosmos that was under no obligation to place anything close to anything else. Consider what that distance means in terms of time. Consider what that distance means in terms of time. It holds within it the collapse and rise of ice ages, the migration of our ancestors out of Africa, the extinction of the Neanderthals, the invention of writing, the construction and ruin of every civilization in the archaeological record, and the whole of everything human beings have ever thought, spoken, built, or remembered. Voyager 1 will travel for a duration equal to all of that, and then repeat it more than 1,000 times over before it drifts into the gravitational neighborhood of another star. No biochemistry survives on those timescales. No biochemistry survives on those timescales. Expose the cellular architecture to the unmodulated cosmic ray flux of interstellar space, where high-energy iron and nickel nuclei carry enough ionizing force to damage a column of tissue in a single pass, and where that damage accumulates across centuries, then millennia, then millions of years. The question is no longer whether the organism can repair the damage. It becomes whether the molecules that carry the instructions for repair retain any meaningful fidelity after 10 million years of that kind of bombardment. It becomes whether the molecules that carry the attempt, so that whatever arrives, if anything arrives at all, is chemistry rather than biology.
Sterilized carbon compounds. Sterilized carbon compounds.
The invisible wall doesn't need to be crossed for the wall to have already won.
It wins by attrition, by scale, by the quiet geological enormity of what an interstellar crossing actually demands from matter organized enough to be called alive. It wins by attrition, by scale, by the quiet geological enormity
that span
of what an
is longer than the entire arc of modern human thought. It holds within it the collapse and rise of ice ages, the long migrations of our ancestors out of Africa, the disappearance of the Neanderthals, the slow invention of writing, the building and crumbling of every civilization that archaeology has ever found. Everything human beings have ever thought, spoken, made, or remembered. It holds within it the collapse and rise of ice ages, the long migrations of our ancestors out of Africa, the disappearance of the Neanderthals, the slow invention of writing, the building and crumbling.
Even that organism exists inside a very specific context: liquid water, enzymatic repair machinery, a continuous supply of metabolic energy.
Take the water away. Take the water away.
Expose the cellular structure to the unmodulated galactic cosmic ray flux of interstellar space, where HZe ions, relativistic iron and nickel nuclei, can ionize an entire column of tissue in a single pass, and let that damage accumulate across centuries, then millennia, then millions of years. The question is no longer whether the organism can repair itself. The question is no longer whether the organism can repair itself. The universe doesn't forbid life from attempting that journey. It simply ensures that whatever arrives, if anything arrives at all, is chemistry rather than biology. It simply ensures that whatever arrives, if anything arrives at all, doesn't need to be crossed to win. It wins by attrition, by scale, by the sheer geological enormity of what an interstellar crossing actually demands from matter organized enough to be called alive. And here is where the deeper meaning of the heliosphere's boundary begins to settle in.
The Heliopause isn't simply a plasma discontinuity sitting out at 120 astronomical units.
It's the outermost expression of a gravitational and electromagnetic envelope that makes the inner solar system habitable in the first place. Without it, the galactic cosmic ray flux reaching Earth's surface would increase catastrophically. The atmosphere wouldn't be enough. The magnetosphere wouldn't be enough.
The roughly 70% of relativistic particle radiation that the heliosphere currently absorbs, deflects, and softens, all of that would arrive unimpeded.
The steady radiation environment at the surface would shift from something compatible with complex multicellular life to something compatible only with organisms living deep in the rock, if anything at all. The wall protects inward just as absolutely as it isolates outward. The wall protects inward just as absolutely as it isolates outward. These two regimes don't negotiate. They balance at a pressure discontinuity, roughly 1.5 astronomical units thick, and beyond that line, the sun's reach simply ends. This is why a biological crossing, in either direction, outbound from the solar system or inbound from another, doesn't just require the right organism. This is why a biological crossing, and in either direction, is systematically wrong for it. And the physics is systematically wrong for it. And then there is the hydrogen wall itself, that vast accumulation of decelerated neutral hydrogen piling up just outside the Heliopause through resonant charge exchange. It's a real structure. It's a real structure. The wall blankets the solar system's outermost edge with dense neutral gas that interacts with charged particles and electromagnetic radiation in ways that further complicate any transit scenario. The solar system is enclosed, sealed from without, by layered, overlapping physical barriers, each operating on a different scale and through a different mechanism, but all of them arriving at the same quiet conclusion: isolation. When Jeff Linsky and Brian Wood analyzed Lyman alpha absorption in the direction of Alpha Centauri, they weren't simply finding a structure around our own sun. They were recognizing something that other stars possess as well: astrospheric hydrogen walls surrounding stellar systems across the galaxy, each one marking the place where that star's wind finally gives way to interstellar space. They were recognizing something that other stars possess as well: astrospheric hydrogen walls surrounding stellar systems across the galaxy, each one marking the place where that star's wind finally gives way of sealed, pressurized envelopes, each one inflated by a different star, each one separated from its neighbors by tens of thousands of astronomical units of cold vacuum, where galactic cosmic rays move without impediment, and neutral hydrogen flows at velocities shaped by the galaxy's own slow bulk motion, paying no attention to any of the small warm lights scattered through it. And so we find ourselves here, at the quiet edge of everything we've ever known. And so we find ourselves here, at the quiet edge of everything we've ever known. Something arriving from another star would face the same crossing in reverse, carrying with it the full weight of geological time spent drifting through exactly that environment.
And then it would still need to pass inward through the Heliopause, crossing against the steady outward pressure of the solar wind, through a boundary that deflects interstellar plasma and filters interstellar gas with quiet, consistent efficiency. And then it would still need to pass inward through the Heliopause, crossing against the steady outward pressure of the solar wind, through a boundary that deflects.
When Jeff Linsky and Brian Wood carried out their spectroscopic analysis of Lyman alpha absorption toward Alpha Centauri, they weren't only confirming a structure around our own sun.
They were recognizing a feature that belongs to other stars as well. They were recognizing a feature that belongs to other stars as well.
Its own termination shock, its own heliopause, its own heliopause. Voyager 1 is out there now, moving silently through the very local interstellar medium at 17 kilometers per second. Its plutonium-238 generators lose roughly 4 watts of power each year. Its plutonium-238 generators lose roughly 4 watts of power each year. But because the wall isn't a barrier in the conventional sense, it isn't a surface to be breached with enough force or enough technology or enough will. It isn't a surface to be breached with enough force or enough technology or enough will.
It is the sum of every constraint the cosmos has placed on the movement of organized matter between the islands of stellar light scattered across the galaxy.
Nothing alive has crossed it. And the physics doesn't make this a tragedy. The physics makes it a fact, as settled and as permanent as the inverse square law, as the rocket equation, as the speed at which a Lyman alpha photon travels from the surface of the sun to the hydrogen wall and back, in a universe that has been running its calculations for 13.8 billion years, and has arrived again and again at the same quiet answer. The wall stands. The wall stands. And the nearest star waits, 4.24 light-years away, as it has always waited. Unreachable, not through any failure of imagination, but through the patient, absolute mathematics of the cosmos itself. Unreachable, not through any failure of imagination. Let it settle, but slowly, like everything else in the dark between the stars. There is nothing left to reach for tonight. There is nothing left to reach for tonight.